Hello all, good morning. This is Dr. S. Subalakshmi, an assistant professor in the Department of Mathematics, SNS College of Technology. This is a lecture video series on the course Matrices and Calculus, and now we are on to the discussion of case study approach on change of order of integration. Now we have our students with a slide presentation to explain the concept very well.
What is change of order of integration? In double integration, double integral r f of x to x y dA. The order of integration refers to whether we integrate. First, with respect to y and then x. Integrate x is equal to a to b, integrate y is equal to g1 into x to g2 x f of xy dy dx. Or with respect to x and then y. Integrate y is equal to c to d, integrate x is equal to h1 x to h2y f of xy dy dx. Changing the order means rewriting the same region R by interchanging the role of x and y without the change of physical region.
So what you say here in the previous slide, here she says about previous slide. Change of order means rewriting the same region R by interchanging the roles of x and y. Just she is interchanging the roles of x and y and getting the change of order of integration. Moving on to the next slide.
Why do we change the order of integration? Change of order of integration is performed when the integral is different or impossible to evaluate, or the region has curved boundaries, or the integral becomes similar in a reversed order, or the applied probability, heat transfer, fluid mass, or mass balance models.
So these are our key points to hold our change of order of integration in place. What are those? Probability,
heat transfer, fluid flow, or mass balance models.
So these are the things we include in our study.
Optimizing heat distribution in a solar thermal collector. The real-time problem context empathy. In the solar thermal power plant, a flat observer plate receives solar radiation.
Here, what they are explaining us, they are just including a real-time application here. That is what our case study is going to have. We are just going to optimize the heat distribution in the solar thermal collector.
The heat absorbed per unit area on the plate varies with the position due to the angle of incident of sunlight, so surface geometry, material coating variation. Here, the engineers need to compute the total heat absorbed over the non-rectangular region of the plate caused by a particle shading and
Structural constraints. So these are the constraints we have. What are the constraints? First one is same
sunlight,
and incidence of the sunlight. Second one is
surface geometry,
and the third one is
material coating variation.
So these are the things we are in need of taking as the constraints and logging as the conditions here.
The observed plate region R is bounded by a parabolic shallow curve caused by a support structure, a linear boundary created by a
Panel alignment. So these are the things we are going to take it off as the constraints and putting it on the double integral over here. So the total heat absorbed is given by this Q equation. What is this Q equation? Q is equal to
double integral R Q of xy
dE into dA. Q of xy into dA. This is what our constraints holds here. Mathematical formulation. It is an initial prototype. Here, using it is an original order. Q is equal to integral x is equal to 0 to 2. Integral y is equal to x square to 2x 1 dy dx. So this is our integral where we consider it as a vertical step. In the previous slide, we have considered one q of x comma y. Now that is what we are given here as a double integral. What is the engineering difficulty? This is what going to explain by our student. It may contain involve exponential or trigonometrical terms. It may difficult to integrate. Yes. Verticalizing lets us to complexity. It basically says that difficult to integrate. So these are the difficulties faced by the engineers. What are the difficulties? Is computational properties are to be integrated here. Integration means difficulty is faced by the engineers using exponential and trigonometrical terms. That is what they have explained here later. Next slide. Next. move on to ideal stage. Here, in this stage, we are going to change the order. By changing the order, we get better alignment with sensor-based scanning in y direction. It is easier to extend to non-uniform heat models. By visual thinking, here plotting the boundaries, y is equal to x square is a parabola, y is equal to 2x is a straight line. By solving this equation, we get x is equal to 0, 2 and y is equal to 0, 4.
So this is what we get as a numerical value. But previously, these are the things we have got as an order alignment. So these alignments requires these kind of numerical calculations, and this is what we infer as a result.
This forms a shaded non-rectangular flow.
So this is what we get as a shaded non-rectangular zone.
Change of order of integration. For step 1, we set new outer limits in y direction. 0 less than or equal to y less than or equal to 4. Next step, set new inner limits in x direction. From line x equal to y by 2 to parabola x equal to root y. Change the order of integral q equal to y equal to 0 to 4 limit x equal to y by 2 to root y 1 dx dy.
So in previous case we have got as the y as the inner integral and x as the outer integral. But here after changing the order of integration we have got x as the inner integral, y as the outer integral. So as usually we will formulate the problem and compute the values. Next slide.
Evaluation. Test the prototype. Inner integration. Integral y by 2 to root y dx equal to root y minus y by 2.
On integrating we will just have the value here. Next.
Outer integration q equal to integral 0 to 4 root y minus y by 2 into dy.
So this is what we get as the values of inner integral and outer integral. What is it form?
Is computationally lighter, aligns with physical heat scanning along time, improves
And it
simulation
also
speed.
improves the simulation speed as well. Okay, thank you. Next slide.
Integration of result, engineering insight. The same physical energy, heat energy is applied. Mathematical representation changes, not the physics. Change of order transforms a complex energy integral into an efficient computation model.
So what is the change of order transforms? It transforms the complex energy integral into an efficient computational model. So this is what we infer as a result for change of order of integration. Now the learning outcome for the students.
The students can correct geometry with physics,
Correlate geometry with physics.
visualize integration as area accumulation, apply change of order of in thermal, fluid and probability problems. Think like an engineer, not just a calculator.
So this is what we infer. This change of order can be applied in thermal engineering, fluid engineering and probability problems also we can apply. So this is how we case study a problem wherein we have maintained